So let's just do a quick kind of review of the example we did in class for balancing equations. So first things first is on scratch paper, you don't have to do it in this document if you don't want to, is write down the different kinds of atoms you see. So we've got carbon listed, and then we have to put it on both sides of the equation, right? Just like in math class. This is the same rules as algebra. So carbon on the reactants and carbon on the product side, oxygen on the reactants and oxygen on the product side, and last is hydrogen. Okay, so for balancing, you can change these spaces in front of a molecule called a coefficient. So first things first, I just like to list how many I see. So over here we've got 1 carbon currently represented, and here we've got 6. These little numbers that come after the letters are called subscripts, and they tell you how many of that specific atom is in the whole molecule. Let's go back now, and how many oxygens do we see right away? We see 1, 2, and 3 on our reactant side. And over here, we've got 1, 2, 3, 4, 5, 6, 7, 8 currently on our product side. So definitely oxygen is going to take some balancing. And last but not least, you see 1, 2 hydrogens and 12 hydrogens in this honkin' molecule over here. By the way, this is one of Miss Duncan's favorite reactions. This is photosynthesis. Okay, this reaction is photosynthesis. So let's just start from the top. So you are always bringing up the side with less atoms. So that's the one you'll change, okay? So right now we've got fewer carbons on the reactant side, so we're going to be playing with the coefficients on the reactant side. How do we make the carbon on the reactant side over here equal to 6? Easy peasy. Add a coefficient of 6. 6 times 1 is 6. Okay. Let's keep going then. Now we've got, because we changed this coefficient and this molecule has an oxygen in it, we have to update this oxygen count now as well. So this 6 is multiplied not only by the carbon, but we have to account for it affecting the oxygen count. So now this is 6 times 2, which is 12, plus 1 more, which is 13. Okay, we've got 13 oxygens currently. Now let's go over to our product side. We need to bring this up. Okay, how do we currently get to 13? If you see weird ratios, kind of like I said in class, 13 over 8, this is going to be really annoying to crunch the numbers. So sometimes Miss Duncan sees weird ratios where the common denominator is not super obvious. Then I'll just skip over it if I haven't finished balancing another atom yet. So right now when I see 13 over 8, I'm like, yeah, we can maybe let the oxygen sit for a minute because I also have to work with hydrogen anyway. And I'm going to be working on the reactant side because this is one that's lower than the products. So let's skip over our oxygen for a minute. Now, going on, we've got our hydrogens. Right now there's 12 on the products side, and we need to bring reactants up to 12. So what times this subscript is going to equal 12? In this case, it'll be 6. 6 times 2 is 12. So knowing your multiplication tables is very helpful. Okay, great. Now our hydrogens are balanced. And the next thing that we'll notice is this coefficient also is affecting the O here. We've got 2 places that have O's in them, and we're accounting for both. So we've got our 6 times 2 is 12. That's our current count. And now it's 6 times 1, or overall, we've got 6 oxygens plus now 12 oxygens, which gives us a total of 18. All right, we're almost to the home stretch. So now we bring up, last step, is the product side, which is now less than our reactants. So the last thing we have to affect here is this coefficient on the oxygen molecule. So how do we get essentially 18 on both sides of the equation? Now, remember, you've got an oxygen in 2 places, so always account for that. Otherwise, you'll end up adding the wrong coefficient here and having too many oxygens. So right now we've got 6, and so Miss Duncan likes to write herself little notes. Okay, the 6 is existing all on its own because it's a part of this glucose molecule. And so now we need to make up the remainder from this 18. So 18 minus 6 is 12. How do we get 12 out of this O2 molecule? Easy peasy. The common denominator, the multiplier to get us to 12 is 6. 6 times 2 is 12. So now 6 plus 12 18. Our whole equation is balanced. Good job. Okay. Let's do another one really, really quickly. Okay, aluminum plus hydrochloric acid. So let's do our counting. We've got one aluminum right now in this equation, and over here we've also got one. Nice way to start. We've got one hydrogen, and we've got two hydrogens here. All right, we'll go back and balance that. And last, we've got one chlorine, and here we've got three chlorines. Ratio alert, we're looking for common denominator, most certainly. All right, aluminum is balanced. Let's go to the next element. Hydrogen is imbalanced, and the reactant side is lower, so the reactant side is what we're going to be adding coefficients to. How do we bring this hydrogen up to 2? We add a coefficient of 2. There we go. 2 hydrogens down both sides. Awesome job. Now, though, this coefficient is also affecting this chlorine because they're in the same molecule. So let's update our chlorine number. And here we go. We've got a ratio alert. We need to find out essentially what our common denominator is between 2 and 3. Very commonly in chemistry, you'll start getting a sense for 2 over 3s and common denominators of 6, etc. Okay? So our reactant side is still lower. And so we need to bring this chlorine number up to 3. So let's see what happens. The simplest thing to do is to actually now change this coefficient simply to 3 because it affects not only the hydrogen but the chlorine. All right, so our chlorines are now balanced, and let's update our hydrogen count. We've got 3 hydrogens and now 2 on the product side. All right, home stretch, we need to find some sort of multiplier that will give us like the balance point between 2 and 3. So you can skip ahead basically, and like our common denominator is bringing this number to 6. Okay, we need a coefficient that's going to equal 6 hydrogens because that's the point where these two multiplications are going to align. Okay, whenever you see 2 over 6 ratios, you're bringing your total numbers up to 6. Okay, so what times 2 will probably equal 6? Is 3 is the only answer. So we've got a coefficient of 3 now times 2. We've got 6 hydrogens overall. Let's go back and change our our coefficient one more time on the reactant side. What will give us 6 hydrogens is just a coefficient of 6. And then our chlorines are now out of balance again, no problem. We've got 6 chlorines now, and so let's go over here. What's our coefficient to get this up to 6 is 2. Okay, so our chlorines are now up to balance, and our hydrogens are left alone. Awesome. Our aluminum, though, is the other thing that changes. Home stretch, last move. We need to balance our aluminums. Easy peasy. How do we bring our aluminum on the reactant side up to 2? We just add a coefficient of 2. There we go. Aluminum and hydrochloric acid equation balanced. So you'll find, for those of you who didn't just stop the video, you're looking for common denominators on either side of your chemical equation. And using multipliers, coefficients, exact same kind of term in algebra, using our coefficients to bring our ratio up to the common denominator, and then essentially updating atom by atom without changing the subscripts. Remember, these little numbers are off limits. We cannot change them. The only thing we can change is essentially adding more by increasing the coefficients next to our molecules. Let's say that one more time. We can't touch the subscripts, okay? These are permanent and basically follow the laws of chemical bonding. What we can do as chemists is figure out the coefficient, and our only power is to add more or increase our coefficients piece by piece to bring both sides up to a common denominator.